Hello everybody, this is Dr. Pennington again, and this is a video that wasn't originally in the list of videos I wanted you guys to look at, but I realized it was one that I needed to add in. This is a video that's a precursor to the video that I'm going to be doing very soon about redox reactions. And the thing that I realized was you guys need a good understanding of how to assign things called oxidation states in molecules before you can truly understand how redox reactions work. And trying to put everything into one video would have made it long and painful. So I decided to split it into two. So this first video is about the concept of assigning oxidation states, assigning charges to species in a molecule or element or ion by itself. And to do this, I'm just going to go through species by species and illustrate a couple of rules to you as we go. All right. So let's start off with chromium here. All right. And as we have shown, chromium is in its elemental form. Chromium is a metal. It's in its natural state. Just as you would say something like hydrogen, that's in its standard state, H2. You know, oxygen is its standard state as well, but when it's by itself and there's no charge indicated. When it's by itself with no other atoms and when there's not a charge indicated, that element, the atom of that element always has the same oxidation state. That oxidation state is 0. All right, and that's one of the first rules to understand. All right. Now it turns out that chromium is the only one of this entire page that has an oxidation state of 0 because it's the only element completely by itself where there's no charge indicated. When we have a metal ion like this, chromium 3+, the oxidation state is always equal to the charge on the metal. So in this case, the oxidation state is +3. And when we look at, let's say for example, when we look at this guy right here, CCl4, that's my email again. Notice there are two different atoms that we need to figure out oxidation states of. Those are chlorine and carbon. All right. The carbon is the one kind of in the middle of the molecule because the 4 chlorines are around it. So we're going to figure out the chlorines first. Now chlorine, if you look in the periodic table, chlorine is in group 7, which means that chlorine wants to have one extra electron to give it its octet. So each chlorine is going to be -1. So what we have here is we have Cl-, Cl-1. And because we have 4 of those, our overall negative charge is 4-, because there's 4 chlorines. And if there are 4 chlorines and the overall charge of the molecule here is 0, because there is no charge indicating otherwise, in fact, as there is a minus here and a -2 here, those mean the overall charge here is -1, the overall charge here is -2. For all the others where there's no charge indicated, that assumes that we understand the overall charge is 0. So therefore, if Cl-, 4 of those Cl- give us a total negative charge of -4, then if the whole thing is 0, then the charge on carbon must be +4. All right, and that's exactly what it is. Now let's go down to the next one, strontium bromide. Now we have a couple of things that tell us what's going on here. Strontium is a group 2 metal. And group 2 metals always form a +2 charge, just as group 1 metals always form a +1 charge. But the other way to tell us that this is actually correct is to look at bromine. Bromine is in group 7 just like chlorine was. Therefore bromine wants to gain one extra electron to gain its octet. Therefore the charge on bromine you'd expect to be -1. But because there's 2 of them, the overall charge for those 2 bromines is -2. So -2 and +2 gives us 0. Remember, in each of these cases, we want the overall charge of the species to equal 0 unless indicated otherwise. All right. So sulfur trioxide here, SO3. We have 2 elements. Again, the sulfur is the central one, so we're going to do that last. But there is one other rule here that's kind of beneficial. Oxygen and hydrogen, no matter what the molecule is, with one single exception, oxygen always forms the same charge, and you can get to that charge by doing exactly what we did for chlorine and bromine. Oxygen is in group 6 in the periodic table, meaning that oxygen wants to gain 2 extra electrons to obtain its octet. Therefore, the charge that oxygen forms is O2-. And that's virtually always going to be true, and we're going to use that rule for all the other compounds containing oxygen. Use it as kind of a shortcut. And we'll get to the rule for hydrogen here in just a minute when we get to it. So if there are 3 oxygens, then the total charge for those 3 oxygens must be 6-. And if I have 1 sulfur, the overall charge is 0, and I have 6- from the 3 oxygens, then that must make my total plus charge on the sulfur to be +6. Let's do the same thing for nitrogen. We're going to do the oxygens first. Alright. Again, we've got 3 oxygens. Each oxygen has a charge of 2-, giving us a total charge of 6-. But the thing we have to take into account here is the overall charge of -1. Now, what that means is the charge on the nitrogen minus the 6 for the 3 oxygens is all going to be equal to -1 or -1. So therefore, not much of a surprise to see that the nitrogen is 5, +5. All right. Now, one thing before we go on here, I just want to make sure you guys understand this. Each chlorine forms 1-. Don't say that Cl is 4-, because it's not. This 4- comes from 4 of these. Likewise, don't say bromine is 2-, because we have 2 bromines. All right, each bromine is 1-. So the one thing you don't want to be doing is saying something like this, because Br2 by itself has a total charge of 0, and that's the only time you'd see Br2 written this way. And that would really be 0. So make sure that you indicate the charge on each ion. Chloride, bromide, oxide. So you recognize each oxygen is 2-. Alright? Alright, let's go down to the next one. Sulfate. Kind of similar to SO3, except there's 1 extra oxygen. This time there's 4 oxygens, each of which have the charge of 2-, giving us a total negative charge of 8-. And so the charge on sulfur minus 8 for the 4 oxygens gives us a total charge of -2. So once again, just as the sulfur was +6 here, it's +6 here as well. Alright, so that's a bunch of ones to begin with. Now when we move over here, we have molecules that are slightly more complicated, but we can follow exactly the same pattern. Potassium, manganese, oxygen. Potassium is in group 1. Its charge is always going to be the same. That charge is always going to be +1. That's always true for elements in group 1, for metals in group 1. Oxygen, we know, is going to be 2-. And because there's 4 of those, that total negative charge is going to be -8. Because there's no charge shown here, what that means is the +1 from the potassium plus the charge on the manganese minus the 8 for the 4 oxygens will give us a total charge of 0. So therefore the manganese, there's only one number that Mn can have, and that is an oxidation state of +7. Let's do the same thing here. This is potassium dichromate. The potassium, again, has a charge of +1, but there's 2 potassiums here, meaning that total positive charge from the 2 potassiums is +2. All right. In the same way, we know the oxygen has a charge of O2-. All right. And there's 7 oxygens here in this case, so that means a total negative charge of -14. So if we do exactly the same thing, we've got our +2 from our 2 potassiums. We have the charge from 2 chromiums, because we've got Cr2, 2 chromiums here, minus the 14 from the oxygens, all equal to 0. If we do the math here, then the 2 chromiums have a charge of 12, which means each chromium must have a charge of 12 divided by 2, 6. Alright, so therefore each chromium has a charge of plus 6. Alright. Now, tetraphosphorus Daca oxide. Looks complicated, but it's just two different elements. Oxygen, we know before, we've said this several times already, has a charge of 2 minus. Therefore, the total negative charge there is negative 20. And so that means my 4 phosphorus atoms have to have a charge opposite and equal to the minus 20, which means 20 divided by 4 is 5, so therefore each phosphorus has a charge of plus 5. Alright, because 4 of them give a total charge of plus 20. Alright. This is perchloric acid. Now this is where we get to talk about hydrogen. Just as oxygen always had that charge of negative 2, and so 4 of them having a charge of negative 8, hydrogen is always in the same boat as well, with no exceptions. Hydrogen only has 1 electron, and in the vast majority of cases what you're going to see is hydrogen forms an ion of plus 1 when it loses that 1 electron. So then what we have here is we have the 1 from the hydrogen plus whatever the charge is from the chlorine minus the 8 from the oxygens, giving us 0. Now notice chlorine down here was negative 1. There's no way you can see that we can't do 1 minus 8 equals 0. So what that means is chlorine has to have a different oxidation number than what it had here. Mainly because chlorine's the central atom here and it wasn't here. Chlorines have a big enough size where it can actually have different oxidation states. And so if we do the math here, what we get is the fact that chlorine in this case has a charge of plus 7. When we go down to our last one here, sulfuric acid. Each hydrogen has a charge of plus 1. But there's 2 hydrogens, so therefore we have a total positive charge of plus 2. The oxygens, as we've seen many times now, each has a negative 2 for a total negative 8. Therefore, the 2 from the 2 hydrogens plus the charge from the sulfur minus the 8 from the 4 oxygens gives us a total of 0. So therefore the sulfur is, we take things over to the other side and do the math as we've done before. Sulfur ends up being plus 6. So it's important that you guys get a good understanding of how to assign these oxidation states, because when we start to do redox reactions, it will be assumed that you know how to do this. So make sure that you know how to do it, otherwise the chapter on the part of the chapter on redox reactions will be a nightmare. So make sure you can do it. All right, thank you.